Hello, my name is Muhammad Faisal. I am a fourth year undergraduate student at IIT Bombay. Today I'm going to set up the model for a base fixed three-story building. Then I will implement base isolation using lead rubber bearing. Then I will compare the responses I got from both buildings. So first of all, I'm going to show the building. So here it is a three-story building of uniform height 4 meter, and two bays along x direction and three bays along y direction. Both are 5 meter distance, and the dimensions of columns and beams are given here, as well as the thickness of slab for both floor and roof. So here is the picture of the base isolator, that is lead rubber bearing. It is an internal view of the lead rubber bearing. I have designed both. I have designed the isolator properties using both non-iterative and iterative methods. I have already found the stiffness and post-plastic ratios and all other parameters related to the lead rubber bearing. So I will use these values in order to run my base isolator model. So later I will compare the results from both methods. Okay, so let's get started with the model. So here is SAP window. So first of all, we need to create new model, 3D frames, three-story, here 2, 3, and the height of stories 4 meter, and bay width along x and y both are 5 meter. Next, we need to define the material, which is concrete, what we are using. So define material. So it's already defined, it's by default. So we just need to check the values whether anything wrong. So these are like density of concrete and elastic, post-elastic, I mean modulus of elasticity and coefficient of thermal expansion all are given. So this is for steel that anyway we are not using in this model. So next we need to define the frame sections. For that, define sections, there is frame section. So we need to add new property. We need to use section design. Okay, first design the beam, concrete, section designer. So the width is 0.3. Done. Similarly, need to create another property. So section design, and let's give the name column. 0.4 or 400 millimeter. Okay, yeah. Next, to define area sections, define section properties, area sections, add new property. First, roof. So it is 0.15 or 150 millimeter thickness. So okay, next add new section which is floor. Yeah, it is 250 millimeter or 0.25. So okay, next to assign the frame sections, assign frame sections. So we need to first we need to select all beams, then we need to assign the beam frame section property. So for that you can use the we can change the view. You can select all beams, beam, apply. Okay. Next you need to select after selecting all columns, just assign the column. Yeah. Next, to assign the area sections, we need to change the view to XY. So this is the roof. So for the draw, cube area draw, and use roof. So here it is basically showing the levels like z equal to at 4 meter. If you go up, you can see 8 meter, and this is the top one, that is the roof. Now we have assigned the area sections. Next we need to define load patterns. Define load patterns. So we need super dead load. Okay, next to define mass source. Define mass source. So modify first super dead load, which is 100%, and for live load 0.5, 50%. Okay, next we need to assign loads on the slab. So for that you need to select all objects at level 3. And assign area loads uniform, not uniform, yeah, uniform shell. Then we need test dead, 6 kilonewton per meter square, and we need 5 kilonewton per meter square live load, and on the roof we have 1 kilonewton per meter square live load and 3.5 kilonewton per meter square base dead load. Next, we need to copy all objects at the level 3, z equal to 8 meter to z equal to 4 meter. For that, use replicate -4. We need to go 4 meter down for level 2. Now everything has been copied to z equal to 4 meter, that is level 2 from level 3. It includes frame, sections, load assignments, everything. To assign the diaphragm joint constraint, go to assign joint constraints. We need to join constraint. We need to add 3 more constraints for second level. Oh no, delete this. Okay, we need to change this to diaphragm. Add new constraint, second, and one more, third, then go to ground level, select all objects, apply. Next, we need to assign restraints for the bottom nodes. Select all nodes at the bottom and assign joint restraints fixed. Next, to define load case, go to define load cases, model, modify or load show load case, and change the number of nodes to 20, and change the eigenvectors to widths, and add 3 more load type, acceleration x, okay. Now we need to save the model. This is base fixed. And now the model is running. now the now the now we can check the model results for the building. For that, go to display and show deformed shape. We can change to model, and for the first mode, so we can see the time period and corresponding acceleration for the mode 1. So it is around 0.70448 seconds, and we can check for the second mode apply. So we will get it around 0.697 seconds for the second mode. We can also get the model shape. Let us check that. So apply. Okay, so change the view. So it is in the first mode, the building is actually vibrating or oscillating along the along x direction. You can see the exaggerated animation here. If you click on this, you can stop it. So it is actually vibrating along x direction. So for checking the second mode, you can go to show deformed shape, and you can second and apply. So for that, you need to change the view. Okay, so here it is vibrating along y direction. In the same way, you can see the exaggerated animation for that. So it is vibrating. And the third for the third mode, you can type 3 here and apply. So for the third, you need to check along. So it is actually vibrating along z direction, along like in a twisting way. Okay, now the model analysis are done. Now let us go to equivalent static analysis. It's a lat it is one of the seismic analysis procedures, and it is the easiest method. So for that, we need to define one more load case. First, load pattern. For that, define load pattern. Before that, we need to unload the model in order to make further changes. So define load pattern. We need to add new load pattern. So it is equivalent static along x direction, and it is an earthquake type load. And we are using, you can see a number of codes. So we are going to use the IS 1893 2002, which is Indian. It stands for Indian Standard. So add. Okay, now we need to modify the parameters for. Before that, we need to modify the parameters. For that, modify lateral load pattern. So along global x direction, and we are using user defined. We have already found out the time period for the first mode, which is along x direction, and it came out 0.7049. Okay, so next we need to create the earthquake equivalent static load case. For that, go to define load case. Load case name EQX. Modify. It's a linear static, and you need to change the scale factor to 9.81. Okay, so we can run the analysis now. Now we can check the total base shear along x-axis x direction using display show table and structure output base shear. So select load case, we need equivalent static along x-axis. So we have around 46,000 kilonewton along x-axis. Okay, let's go to response spectra analysis. For that, first we need to create the function responding to response spectrum. For that, go to first we need to unlock the model for further changes. So define functions response spectrum and select the IS1893, add new function. So we have soil type, it is 2, that is median type, and we have seismic zone factor, which is 0.3. Seismic zone 5 is actually the most prone area for earthquake, so it is 0.36, and damping the ratio 0.05. Now we need to create the load case. For that, define load cases, add new load case. You can give response spectra x-axis, and here also we need to change the scale factor to 9.81. No, we need to change the load name to first load pattern to acceleration. Before that, we need to be here, we need to change it into response spectrum, and around x-axis function name function 1, scale factor 9.81, add. Okay, now we can run the model. Now we can check the total base shear using response spectra analysis using display show table. We can select response spectra also. So we get around 4400, here 4600, there is a little variation. Now done. So for time history analysis, we need to scale the ground motion to design spectra. So I have done a separate tutorial for that using Seismomatch, which is a scaling software. So I have already scaled. I will show it in that video how to do that. So I will use directly the scaled ground motion. So for that, I need to create one more function. So define function time history. So before that, I need to unlock the model. Function time history, add new. No, before that I need to change the cosine to from file, add new function, browse. This is the scaled ground motions. This is the difference between, the time interval is 0.005 second. Okay, Okay, let's change the name to time history. Next, need to define load case. For that, define load case, add new load case. Let's create time. So time history analysis along x-axis. We need to change the load case type, which is time history, non-linear, and the time scale factor should be 9.81, and the function time history analysis, time history function name, x-axis, and we need to change the number of steps around 5500. Okay, yeah. So let's run the model. And structure based shear, we need to check the load case, time history along x-axis. Yeah, so done. Now we need to do the analysis, all three seismic analysis and model analysis for seismically based isolated structure. For that, we need to we need to remove the restrainer on on the bottom to lead-rubber bearing. We need to implement lead-rubber bearing, and we need to run all three seismic analysis and model analysis. So for base isolated structure, I'm using the same model for base fixed. So I I'm gonna make some changes for that. Let's change the view. This is level 3. Just copy all objects. We need to use the replicate, and -8 meter. You need to copy all objects in level 3 to level 1. Apply. Yeah. Next, we need to define the isolator properties. So here we have already designed the isolator property. So we are using lead rubber bearing. So what we basically do is we will find the total superstructure mass, and we will divide it into number of columns. That is, here we have 12 columns at the ground level. So we will divide total superstructure mass by the total number of columns, and we will assume that as a single degree of as a mass with single degree of freedom, and the corresponding stiffness will be, we will assume the stiffness for the seismic isolator. So we have already designed those parameters for the isolation system using non-iterative and iterative methods. Here iterative method gives more accurate results, so we use these parameters for our model and we will run it, and finally we will find the time periods for the base isolated structure, and the base shear from each seismic analysis procedure. Yeah. So to define isolator properties, go to define. Oh, before that, you need to unlock. No, it's already unlocked. So define section properties. We have link or support properties. So we need to add new property. So here we need to change the support type to lead rubber, lead rubber isolator. Let's use LB lead rubber BI. So properties along x-axis, I mean along vertical, this is vertical. So you can use these stiffness, which is 18. We need to use in kilonewton, actually we have defined in such a way. And 0 effective stiffness, damping ratio 0. Here we are using nonlinear analysis along x-axis and y-axis, that is two horizontal directions. So effective stiffness, here the units are in Newton per meter, we need to change it into kilonewton per meter. So to assign the isolators, first we need to delete the restraints and we need to assign, then later we assign the isolator to bottom nodes. So we need to use draw one join link. Next we need to define model case. Define load cases. Model load. Okay, well, correct. So let's run the analysis. So we can check the time periods using display and the show the form shape using model. So the time period for the first mode of the base isolated structure is 1.9. So first of all, let's compare the time period. So initially we did the seismic analysis, the model analysis for base fixed, which is points. The time period for the first mode was zero point 0.7 seconds, and the second mode was around 0.69 seconds. And when we isolated the base using lear-rubber bearing, we got the time period. The time period actually increased more than double, around 3 times for the time period is actually increased. So, and we can check the base shear for that table. Base shear, we can select all three seismic analysis procedures which we have already defined in the first model, which is for base fixed. So now we can see the difference. So here the force actually reduced to, it was around 4,000 and now it is around 2,000, so it actually reduced 50%. And the shear force using equivalent static is not changed because we need to change the time period, because which is depends on the time period. So it is around 1.9. So first we need to unlock the model and go to define load case and equivalent static along axis, and so these are okay. We need to change the load pattern actually. So equivalent modify lateral. So here the time period, this is for actually for base fix, we need to change it into around 2 seconds or 1.9 seconds, so which is for base fixed, base isolated structure. So now we will get the correct shear force using equivalent static analysis. So now we can see it has reduced. So now let's compare the results we got from each seismic analysis procedures. So before comparing the result, I will show how we can generate generate the results from the model. So for that, if you need the displacement at the top point, just click on the join where we need to find the response, display, and show table. Now let's find the displacement at that point. So mark this is relative displacement. If you want absolute displacement, you can use this. And time history, we need to select the seismic procedure here. So now we have the displacement here. So this is the displacement along positive x direction for the time history analysis along x-axis. So we can just copy using Control C, or we can directly export the table to Excel, or simply we can just copy using Control C, and I just using Control C, and we can directly copy to database, I mean any Excel file. So from here we can, this is the time, we can see it here. So this is time step. So these are the corresponding displacement along x-axis, these are along y, and correspondingly. So if you want to find the maximum displacement, we can find using equal to max of that vector. So that can be done. Similarly, we can find the acceleration. Similar way, we can go to show table. We can mark the velocity and acceleration. We can mark the absolute acceleration and corresponding, if you want the acceleration in each step, we can use this. If in case if you want the maximum and minimum, we can use the envelopes. Similarly, we can copy the result, or we can directly export using file export current table. So in case if you want the element forces like base shear in this specific column or this column, we can just mark that, we can just select that column, and we can go to display and show table, element output, we can use frame output, and we can use frame element forces. If we need stresses, we can use these. So here we can see the forces. P is actual force, V2 is V2 and V3 are horizontal force, that is the base shears, and this is axial force, compression or tension. Similar way we can copy these into an Excel. So we have already seen that the time period has been increased tremendously. So 0.7 second has become 1.9 seconds. So in design spectra, actually the coefficient, acceleration coefficient, has reduced tremendously as the time period increased. So let's compare the first seismic analysis procedure, which is equivalent static analysis procedure. So the total base shear for the base fixed structure was around 4600 kilonewton, which has become around 2300. So almost nearly 50% reduction in the base shears. Similarly, in both direction along x-axis and y-axis, which both have reduced to around 50% reduction can be seen in both. So in the second seismic analysis procedure, which is response spectrum analysis. So here also we can see that the around 50% reduction in the base shear, total base shear in both direction. So even in the time history analysis, we can see a huge reduction, which is like the 4400 has become 1200. So we can see around 75% reduction. So anyway, response history analysis is the most accurate and time consuming, as well as sophisticated analysis procedure, because we produce the response of the structure at each instance, and these are the highest values from all the responses in each time interval. So we can see the comparison here. So another noticeable thing is in the base fix we cannot see much difference between the total base shear from which are found from different seismic analysis procedure. There is very little variation. At the same time, when we compare each seismic analysis procedure performed for a base isolated structure, there is a huge variation between linear, static, and time history, and response spectrum and time history. Because response spectrum, time history analysis gives the least value. So other two, which shows that which other two seismic analysis procedures are not that efficient in giving the accurate results. So another one is, so here also we can see these are the relative displacement of the relative displacement of bottom and top points of base isolated structure. So these are a comparison between displacement of base fixed and base isolated structure. The 11 centimeter was the maximum relative displacement between top and bottom point. At the same time, when we base isolate the structure, it has become 6.22 centimeter, which has reduced around 50 percentage. So another noticeable thing is acceleration. That maximum top acceleration, top means the acceleration at the top point of the building was around 10.96 meters square per second, which has reduced to 2.94. So it's a 25 percentage of the base fixed. So it actually a huge benefit when we design hospitals or any industrial building where the where we have any acceleration sensitive machineries which might be costing, you know, the major which might be the major cost. At the same time, structural component won't cost that much. So it creates a huge financial loss during an earthquake, especially in hospitals and industries. Finally, what a base isolation basically do is it reduces the base shear and elemental forces and absolute accelerations as well as relative displacement during an earthquake. So overall, what it gives is it protects the structure integrity and sensitive acceleration sensitive machineries during an earthquake. Before performing the time history analysis, we need to uh, scale the ground motion to design spectra corresponding to our seismic zone. So for that, I will first show the plots. So here is the ground motion scaling. So the target spectra is actually corresponding to zone 5 and type 2 soil, which you can see here, the smooth curve and the color, and you can see the original spectra and the matched spectra. So the blue one is corresponding to the original ground motion, and we need to scale it into to corresponding to this design spectra. So for that, I'm here using the software Seismomatch, and the spectra target spectra is IS 1893 based on IS code 1893 and zone 5 type 2 soil. So for that we need Seismomatch. So first of all, I'm going to open the original ground motion. So BTP. So So this is the original ground motion. Let me open that. So here we need to give the time step, and first line we don't need to skip first. And yeah, so this is the original ground motion. So we need to define the target spectra. So IS 1893 zone 5. So this is the target spectra. So we need to change this because our time period might come nearly 2, so let's increase it into zero point 0.4 maximum, and the minimum it won't come that low value, so let's increase to 0.15. So the scale factor, let's give it 2, and tolerance 0.1. So we need to increase the eigen value 0.01, which is enough. And you can check a maximum iteration 30. Yeah. Let's run it, do matching. Now it is converged, so we can see the spectra here. So we can see the matched spectra here. So here we can see the corresponding, we can see the comparison. So the red color is for the design spectra, and the violet one is for spectrum from original accelerogram, and the green one is for spectrum from matched accelerogram. So we can actually copy these values from here, and we can paste it on Excel, and later we can plot this way. So that how we scale the ground motion. Then now it is ready to use for we can copy the acceleration, the time and acceleration from here. And now it is ready to use for time history analysis.